N, and here, so the constant here, and also we'll use the notation for symbol zk. Say I will suppose that it's from little to little L2, so it is from L2 on the unit circle. And so the question of interest is the spectrum of T, this finite section of the big Toeplitz matrix. The big Toeplitz matrix is what? It is just a not the infinite matrix like this, and which correspond to the operator T of phi p plus the projection on the positive indices coefficients of this product, say for polynomials, analytic polynomials. And so initially the question arises as an illustration to Hilbert spectral theory of self-adjoint operators. So in the beginning of 20th century, from 1901 to 1905, Hilbert gave some famous course of self-adjoint operators where the theory was created, but there was not so many examples. And Toeplitz arrived in Göttingen and took just this question to find some examples to illustrate this spectral theory. And so he considered in principle the real valued function phi, so the self-adjoint matrices, and the question was to identify the spectrum of the limit of the infinite operator. And so the finite matrices was used to approximate this spectrum of the limit operator. And let's consider exactly this question: what can be the limit of this the spectra of finite sections of this infinite matrix? So naturally, it's natural to assume to have a conjecture that it converges to the spectrum of the whole matrix, which happens sometimes. But we can look on this figure in a different way. So say in the situation of Toeplitz in the beginning, when phi is real, what is the spectrum? The spectrum is defined then by the quadratic form. The spectrum of T phi n is defined by the quadratic form phi p, where p vary on the polynomial of degree n, and to find say the first eigenvalue, we just need to consider the minimum of this on the unit sphere, then take orthogonal complement, the next minimum, and so on. And if we consider here, so we are not located in this corner, because it's Toeplitz matrix, and this matrix can be shifted on this. Moreover, we can consider yet another operator, just multiplication on the set of all polynomials, not analytic polynomials, but just minus nn, ak, zk. Then we obtain as a matrix of such multiplication operator and infinite Toeplitz matrices with the constant numbered by z times z on the square here. And we will obtain the same quadratic form if we take, say, the matrix here from n equal to 2m plus 1, from minus m to m, and so we identify the spectrum of this matrix to the spectrum of this matrix, and it converges to what operator? To L phi. So we can also wait that this will converges to the spectrum of the multiplication operator, and this is not the same. We have the inclusion, but not normally not equality. And what is the choice? What is more probable? What is the opinion? Where is the truth here? Where it is? It is in a row. I mean, in the sense of convergence. So, and I will show, and we will see that if we consider the convergence as Toeplitz considered from the beginning, and in many other applications, if we consider the statistical convergence, so where is the most part of the eigenvalues, so it converges to the multiplication operator. But if we consider the uniform convergence for the Hausdorff metric between sets, so the distance, it converges to this operator. Why there is no any intermediate? I don't know. Because in principle, I repeat that even for real valued function where the difference is big, because say if the real valued function takes two values, lambda mu, so is the step function. So the spectrum of L phi is just this 2 point, of course, and the spectrum of the Toeplitz operator is the whole interval. And so for statistical convergence, we will have many eigenvalues here, but with the density 0, because the convergence for this in the statistical sense is just to 2 points lambda and mu. We will see the both effect just now immediately. So let me start after this with the determinants, because determinants is a principal tool to study the spectra of Toeplitz matrices. What is determinants? So we have, say, some vectors in a Hilbert space. So we can say n-dimensional, or in some dimension. We can consider the corresponding matrix, say, in developing in some orthogonal basis in the linear hull, and consider the determinant of this matrix. Okay, and what is this determinant? This is the volume of polytopes generated by this vector. So P is the sum of Tj xj, 1 to n, Tj between 0 and 1. The easiest proof is what? Is just the formula of changing variables with Jacobian. If you consider this mapping, which take Tj in this sum, so the Jacobian is just this matrix, and so you have by the changing variable this formula. In particular, from the same geometric meaning and from, say, Fubini formula, we can take that the ratio, if we add some element x to this xn and one more x, so we will obtain that the ratio, and this is, say, non-zero, then the ratio of this tricks is equal to what? it is equal by, so say, here we have xj, here we have x, so the polytope is here, and here we have the volume of this polytope, and here we have the volume of this polytope. So by the formula, this is just the height. Here, so the distance of x to the linear hull of xj. This is an easy known formula, of course. And what happens if we go to the gram matrix? So the gram matrix of the system xj, this is just xi xj, say from 1 to n, and this is what? This is, we can say that this is the product of two matrices. This is x1 xn to the, no, I'm sorry, to x1 xn as lines by x1 xn in this direction, and so the determinant of this gram matrix, this is just the product of this one, so the determinant of x1 xn square, okay, because it is scalar product corresponding, and so we obtain in particular that the distance of x to the linear hull of xj squared is equal to the ratio of gram determinants of system xj plus x to the determinant of the gram matrix of xj. I will use it immediately to compute the Toeplitz determinants here. So I use the same notation as before, dn of phi. This is the determinant of ai minus j from 0 ij to n. So n plus 1 by n plus 1 matrix, where n vary from 0 to grow from 0 to infinity. And so we have that from this formula, we have that, so we suppose that dn of phi is positive. Say I will consider not phi maybe, but just a non-negative measure. So ak are Fourier coefficients of a measure, and mu is non-negative measure, and it is not, I suppose that it is not a finite combination of atoms to have that all these determinants are positive for every n. And then, so from this formula, we can have that dn over dn minus 1 of, so phi equal to mu, so I will write mu, is equal to the distance in square of z to the n. So I apply it, what is, so I'm sorry, it's maybe I just not write that this is a determinant of what? This is a determinant of the system zk 0 to n in the space L2 of mu, okay? Because this is a matrix zk zj in L2 of mu, which is mu k minus j, okay? So this is the gram matrix of the monomials in the space L2 of mu. And so this is we have this formula, and so this is the minimum of integrals Zn minus p squared d mu over all p of Pn minus 1. And so we can multiply by z bar and replace this by this one and take yet another complex conjugate, so 1 minus Zn p bar square. And this one run in u over Pn. Okay? So this is in fact over Zpn. And so we have that Zpn minus 1, I think, however. So we have the minimum of 1 minus Zq squared mu, where q run over p n minus 1. So we obtain this ratio is a monotone. It decreases. It decreases and has a limit which is equal to the distance from 1 to the all analytic polynomials, equal 0 at 0. So we obtain that dn over dn minus 1 is decreasing and tends to the infimum 1 minus Zp square d mu over all polynomials p, which minimum we know. So I will use, of course, the Verblunski theorem, 1920, 1936, which says that this is equal to the exponential integral logarithm Radon-Nikodym derivative of the measure. So mu is equal to w m plus singular component, and this is exactly w. Not this, but this derivative is exactly w. So we know this limit here. And so now we consider, so I forget an interesting example. So we have some limit theorem already. So we have, I can state it as a theorem. This is Seguin theorem that whatever is the positive measure, there exists a limit of dn over measure which is not a finite combination of atoms, dn minus 1, which is equal to this g of mu, which is by definition this geometric mean of absolutely continuous component, which is just by definition this integral log w dm. And so we will transform this formula in a limit distribution of the spectra. How we will do it? Just by the definition of the determinant, we can rewrite first of all it in the form because if a sequence converges, so the arithmetic mean converges to the same limit, and so we have that the limit of dn 1 over n plus 1 is equal to g of mu. It is a consequence direct of this formula. So I rewrite it in U. dn 1 over n plus 1 is equal to g mu for every measure mu. And so let transform this formula in the limit distribution of the spectra. So how we will proceed? So we consider not an arbitrary mu, and even not arbitrary absolutely continuous measure, but so where w is non-negative and integrable function in general, but we consider so real valued and bounded from above and from below. We consider this condition, which was the Séguin condition when he started this business, and so apply this result to phi equal to 1 plus uw, where u is real valued and small number. Okay? Then this function is positive, and we can apply this trick here. So we obtain the dn 1 plus uw 1n plus 1. It is the g of 1 plus uw. Okay? So how we can rewrite it? We can rewrite that the arithmetic mean taking just logarithm. Okay? That the logarithm of 1 plus u lambda and j. What is the determinant? Determinant is the product of eigenvalues. I denote eigenvalues lambda and j here, so j from 0 to n, and this tends to the integral of log 1 plus u w dm. Okay? Now we can look at this formula and use the parameter u is arbitrary. Okay? To easily manipulate with this trick, we need some definition which go back to Hermann Weyl, and is exactly the asymptotic equivalence of sequences or measures. So we will take that we have some sequence of T and J, some sequence of n tuples of real numbers, and we will say that and we have some, so I'm sorry, where they are. They are on some interval here, and we have some subset of the continuous functions on the interval. We will say that the T and J asymptotically weakly converge to so in the topology induced by F, so M F to a measure to a function, what is the notation? W is here to the function V. say if we have that 1 over n plus 1 summation f tj tnj to n tends to the integral of f v dm over t, which is in fact the integral of f d lambda v, where lambda v is the inverse image of the Lebesgue measure with respect to this mapping V. I mean, the measure of the set A is the Lebesgue measure of x such that Vx belongs to A. So the inverse image of Lebesgue measure. And so for every small f from the capital F, it simply means that the measure, the delta measures in T and J with the equal masses 1 over n plus 1 converge weakly with respect to this set of function to the measure lambda v, of course, nothing more. And from this definition, it is clear that if this is true for some set f, then it is true also for the span from the closed linear hull of in the space CAB of this V, because the both parts are linear and continuous with respect to uniform convergence. Okay, so we'll use it here because we can look on this what is written here. If we introduce the function Lu of t is equal to logarithm 1 plus tu, so we can consider this equality which is written here as exactly this one, when the capital F is just the collection of Lu, u less than epsilon. Okay? So we can replace it, keeping this limit condition for by the say set script f, which is the span of this capital F. Okay, and I'd like to say that this span is equal simply equal to C naught AB, where C naught is all continuous functions which are equal to 0 at the origin. If the origin is an interval AB, if it is outside, so it is just C. Because of why this is the case? Because of the completeness of polynomials, of course. Because if we take a measure, nu on the interval AB, which is orthogonal of all Lu, what we will have? We will have logarithm 1 plus ut d nu t is equal to 0 from u here. We developed in the series of minus 1 k ut k, and we have from here that integral tk d nu is equal to 0 from k from 1 to infinity, from 1 and so on. So we obtain from Hahn-Banach that every measure which is orthogonal to all Lu is orthogonal also to tk. So tk is in the span of capital F, and so C naught is in the span in view of Weierstrass theorem, and vice versa, of course. So we can take arbitrary function, and on the other hand, for the constant, we have, of course, just equality, because this is equal to 1, and this is also equal to 1. So we can we can conclude, and this, so I prove the theorem, which I know will state, that whatever is the function, a function phi bounded from above and below, so the theorem, and this is the classical Séguin theorem of 1920 or 25, which says that if phi is such kind function measurable, then so we have that 1 over n plus 1, the f lambda nj. Lambda nj are eigenvalues of the corresponding truncated Toeplitz matrix tends to integral f composition phi m for every continuous function on interval AB. And moreover, of course, we can continue a little bit. We can continue, I mean that if f is not continuous, but say piecewise continuous, or just belong to the closure of piecewise continuous function, but which is continuous in any point of the point spectrum of L phi. So it is continuous at any point lambda, such that the measure of the inverse image of the point lambda is positive. So if f is continuous at every such point, we have only at most the countable set of such points. Then we can replace continuous function f by this step function, which is continuous here, in particular by the indicator functions, where alpha beta are not the points of this kind. And then obtain simply that 1 over n plus 1, the number of lambda nj which are in between alpha beta tends to the measure on the Lebesgue measure of the point on the unit disk where phi is between alpha and beta. So the limit distribution is phi, okay, which exactly confirm what I claim in the beginning, that the spectrum T phi n converge to, in this weak sense, in this statistical weak sense, to the spectrum of the multiplication operator. But in the uniform, for the uniform convergence, it converges to the spectrum of Toeplitz operator, however, because, say, for real, it is quite easy to prove, but if phi is real, then the spectrum of Toeplitz operator is just the convex hull of the image of phi. So, say, if phi takes the values on AB as before, 0 and A and B are real values of phi, I mean in the sense of Lebesgue. So it is the whole interval, even if phi takes only two values, A and B. Okay, this is the spectrum. And what happens with the spectrum of T and lambda, T phi n? I mean that in the uniform sense, it converges to AB, because this is self-adjoint operators. Self-adjoint, and so say if for self-adjoint is easy to see, and if we have some lambda here which is separated. So from self-adjoint, I'd like to say that the distance of lambda to the spectrum, phi n, is equal to 1 of the norm of the resolvent. Okay? Because it's self-adjoint. The norm of the resolvent is equal to the distance to the spectrum. And so if this distance is separated from 0, so the resolvent are uniform bounded when n tends to infinity. And it implies immediately that lambda is a regular point for this operator. Okay? So it means that, that in the uniform sense, say the distance between T phi n and sigma T phi in Hausdorff sense tends to infinity. What means Hausdorff sense? So you know it is the maximum of two distances. The two sets are close to each other in Hausdorff sense if any point of one set is sufficiently close to the second set and vice versa. So it is a maximum of what is infimum, no, maximum of distance xb, x in A, and maximum distance y A, y in B. Okay? So in this sense, this reasoning shows that this distance tends to 0 where we consider the larger set of sigma of T phi. I recall that it is easy to see that we have this this inclusion. How much time I have? Huh?
10 minutes.
10 minutes. Okay. So what else? What else? What else? Yeah. So for the most of applications, this theorem gives almost nothing, because in applications the symbol is not real. It is a very specific case. In say what I will speak tomorrow in the third lecture for statistical physics, phi is always complex. And so how to proceed for complex symbols? Nothing from the previous technique will work, because I started with the Gram matrix, which is positive, and so on, which was based in the positivity of the symbol. So for complex, we need to change completely the technique. And there is many techniques to treat a complex case. So the complex case so phi will be yeah will be the complex valued bounded function, and we consider the following procedure, so-called circulant approximation. Circulant matrices which will give the needed result. So the result will be the same. Huh? So it's the conclusion will be the same, but how to prove it? So start with the circulant matrices. What is circulant? circulant shift, first of all. So we consider the cyclic shift operator on polynomials. So in the following way, so we start with multiplying by z, and then to z to the n, and then to 1. Okay, so cyclic. And so the matrix of this operator is n plus 1 by n plus 1 matrix with the 0 diagonal, 1 the under diagonals and zeros, and that's just 1, and the all other elements are 0. Okay? So this is Cn, this is the unitary matrix. Unitary matrix with Cn n plus 1 equal to identity. So the eigenvalues are epsilon and j with j equal to the roots of unity, n epsilon n plus 1 equal to 1. And so unitary. And if we consider the Cn square, say, what happens if we consider Cn square? So the diagonal will move. So it will be 0. It became 0 here, but 1 on the next one. And here it became 0, and then to 1, 0. If we consider Cn3, so this diagonal will move up, downstairs, and this one also will move here. And so if we consider the all possible combinations, so AK, say, CNK, the same for with negative, because negative is, we use this one, so Cn minus 1 is equal to Cn to the n, okay? And so we can consider this combination, and this is called circulant matrix. Circulant matrix. What is this matrix? How we can write it? So it is A naught here, A naught, A1, A1, A1 here, A2, 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 and so on, up to AN, and here is AN. Okay, this is a circulant matrix. What is its principal property? The principal property is that this is a function of a unitary matrix, so it's normal matrix. And say, if I denote it by FCN, F is the corresponding polynomial, so we will obtain that the eigenvalues of this matrix are the functions, are the functions of the values of this polynomial on the roots of unity. And so FCN with the same eigenvectors, this is the F epsilon and k, xk. By the way, what is xk is easy to see for the initial matrix, that this is also the epsilon n j k j from 0 to n. And the corresponding, if we consider these vectors as a column of a matrix and divide it for 1 plus 1, it will be the unitary matrix, which is called discrete Fourier transform, and which diagonalize all circulant matrices. So F d Cn F d minus 1 is the diagonal matrix, 1 epsilon 1 and epsilon n to the n, 0 is 0, and all is clear. So the spectrum is clear, the spectrum of all circulant matrices is clear. And So now we can use it to these circulant matrices for which what we have for circulant matrices, by the way. It is Toeplitz matrices. So what is 1 over n plus 1, the trace of FCN? I mean 1 over n plus 1 summation f lambda, lambda nj, where lambda nj are epsilon a j, the roots of the unit. What is this? This is the Riemann sum for the integral of f over the unit circle. So it tends, of course, at least for f continuous or Riemann integrable, to fdm. Okay? And this is a key observation. Now we will approximate arbitrary Toeplitz matrix by circulant matrix. How we will do it? So t phi is given, t phi n is given. How we will do it? So first of all, we replace phi by a polynomial. So phi by phi L, which is, say, some polynomial which is an approximation to phi. Hey, the better takes just a fair polynomial. Huh? Fair polynomial of degree L of this well. L will be fixed. So L is small, n is big. And then we consider phi L of Cn. What is it? It is just so phi L, this is summation ak zk minus LL. AK is equal to 1 minus k over L phi hat k, okay? Because this is a fair polynomials. So here we will have a bent part of this of the size 2L plus 1 from here 1. Then we will have 0 because the order is n. N is big. N is much bigger than L. Okay, and then because this is a circulant, so we need to repeat here in the corner. In the corner will be repeated the upper and lower diagonal parts here. So I'd like to say that this is a good approximation to the matrix T phi n. This is a good approximation. In which sense that T phi n minus phi L Cn in the Hilbert-Schmidt norm is small o of n. If L at least less or equal. Better L is small little o of n, but it's also enough. It's very easy to calculate. So because Hilbert-Schmidt norm, we can have all summations, and we'll see that this is the case. And if this is the case, so we are done, because the trace of a matrix is summation of the diagonal elements to 0 to n, which is by Cauchy inequality less than n plus 1 the Hilbert-Schmidt norm of S2. Okay? And so using it for with this inequality, we will have that the trace of phi of T phi n minus trace of phi L Cn is less than is what? Is yeah, is small o of is what I'd like to say is that this is square. You can see in square. Okay? So this is small o of n with this, and so the normalize plus 1 summation lambda and j minus the n plus 1 phi l epsilon n j by j. This is small o of 1. Okay? So this limit exists. It is equal to the integral of phi l over the unit disk. And so this limit also exists and also equal. Then we can repeat by the powers. No problem to do it. So for polynomials here, and then take L to infinity, depending on n. And this is finish the proof. That for a complex bounded function, we have the same formula, but for which f, so we will have just last word. We will have this weak convergence, which converge to the integral f phi dm, for which f? For f, which are uniform limits of polynomials. Where? On the spectrum. On the spectrum of what? On the spectrum of T phi and T phi n. And this is the convex hull of the image of phi, unfortunately. So, in principle, this is the polynomials with a holomorphic inside of this convex hull. And so the meaning of this weak convergence is a little bit weak because, say, some arithmetic mean theorem that the integral of the harmonic function on the unit circle is equal to the value of the origin, it is inside of this formula. So this approximation quite weak, but it's called weak. Huh? It is a weak approximation over the uniform limits of polynomials which you need to compute each time when you have an example. Thank you.